Among my favorite sophisticated words in English is defenestration, and you can ask Jan all about that. It's very fancy stuff and funny stuff, or like insanely unfunny stuff. But nevertheless, in this lecture, I won't be speaking about that stuff, but rather of Fraunhofer diffraction, which is also pretty cool things, and lots of things you can Google about it and learn about it in the internet. But you will also learn something about it during my lecture, so I will be introducing to you now the Fraunhofer diffraction, and essentially this is the far field approximation for solving the general diffraction integral we just outlined in our previous lecture. So I will solve the general diffraction integral. Basically, we started by applying the Huygens-Farner principle in our situation, and I will solve it under the approximations that we have a field that is far away from the aperture. And after quite a bit of a lengthy derivation of mathematics, I will end up with a resulting simplified diffraction integrals that correspond now to the Fraunhofer diffraction integrals, and then I will give two different interpretations of these integrals. So I will be speaking about the kind of physical insights that we learn by looking at these integrals, and we also learn something about the mathematics, so we also can understand things and appreciate things from their mathematical point of view. So this is what I will be speaking about in this lecture. So please, lo and behold, a picture that actually shows us the coordinates and how the aperture function looks like, and this is the kind of situation that we are now interested in solving. This is our problem at hand, and we are considering a Fraunhofer diffraction. So essentially, the location point, the observation point of interest, denoted here with the capital symbols. This is far away from my aperture function, and this is denoted with this blue rectangle here. Wave is assumed to propagate along the z direction, as many times that is the case, z as in propagation, and here it's basically facing an opaque screen at the plane of z equals 0, and then only a tiny portion of the slit or aperture is open for light to propagate through, and then the size is of the order of a here. So basically a corresponds to the kind of width or rough radius of the aperture here. The aperture S is basically in that location, z equals 0, and that provides us a possibilities of light propagating through and also diffract. The dimensions of this are of the order of a, as I tried to explain it already to you a minute ago. And then we are assuming that, or we are placing our origin of the coordinate system, XYZ coordinate system, at the center of the aperture. Sometimes, of course, with a very arbitrarily shaped aperture, it might not be clear, but on the other hand, it doesn't really matter like where in the end we place the origin. But in the case of a rectangle and spherically symmetric objects such as a circle, we definitely can appreciate the simplification when we put the origo into the center of the aperture. And now looking at things on an XYZ coordinate system, the surface element ds, we can simply write that to be dx and dy. And this is now the kind of surface element that we are integrating over. The observation point R, denoted with the capital X, Y, and Z. This is in a plane, and z equals z, which is constant, so far away, essentially here somewhere. And we are interested not on a kind of looking at a curved observation plane, but rather a plane where z coordinates actually a constant, so just like a single plane here in a given z plane, z location here. And the observation point, it's always considered that it's far away from my aperture. So that's the kind of regime of approximation when we are dealing with the Fraunhofer diffraction. The distance between a source point of a new wave, essentially, so now we are looking at where the new wave originates, so our prime location, that's denoted with the small variables, and we assume that our location of the aperture is the z equals 0 plane. And the observation point that is far away from the r prime, the capital R, is denoted with this. And now, essentially, and let me still show here explicitly, so that the r prime is essentially the position vector from our origin into the location from which we are calculating the circle wave originating into this point here. So this is how we do things, and ds here is basically the small differential area corresponding to this given point, and here r vector would be the difference in here. And capital R is essentially the location from our origin, the position vector into this point x, y, z. So the length or the distance, basically from our location where the plane wave originates and propagates into this point. This length is essentially scalar r, so we are calculating the absolute value of this position vector r here, and we are interested in that because that gives us the means to calculate the phase evolution of my scattered field or emitted field. So scalar r is basically the difference between the r vector and the r prime vector, so the modulus of their difference. So essentially it's the square root of capital X minus small x squared plus capital Y minus y squared plus z squared, since we just don't have anything here in any plane other than z0 at the object plane. And this is inside the square root. And this we must approximate, because we cannot otherwise analytically solve the diffraction integral. Of course, numerically we would be able to do that, but we do not want to do that. Instead, we want to do analytical calculations here, because that then provides us a better physical interpretation and understanding of the situation, and not just doing numerics. So we assume that the observation point capital R is far away from the aperture, like I've said. So essentially this term 1 over R is almost a constant, and it's almost 1 over R. So that helps us in simplifying the diffraction integral. More on this later when we're actually having time to look into that again. So we must approximate the phase term. So essentially the exponent IKR term inside our general diffraction integral. And how do we do that? Is that we can start by squaring the R, so that we don't need to deal with the square root of the right hand side. So we have this guy, which is essentially exactly the equality we had in the previous slide. And now we just squared both sides. And now we can write the squares of x's and y's out. And what we get is that we simply have x squared minus 2 times xx plus small x squared. And then we have the capital Y squared minus 2 times capital Y times y plus small y squared. And then we have the z squared capital Z. And we can reorder groups, reorder the terms. So we see here that we have the capital X squared, we have the capital Y squared, and we have the capital Z squared. So of course, this is essentially the capital R squared. So we can definitely simplify our bits and pieces like that. And then what we have left is we have the squares of the small x and small y. And then we have the two minus terms. So we have minus 2 times xx plus yy. And now we can turn this into a different form. So we take R to be a common multiplier of all of these terms, because it helps us to simplify things, approximate things in what follows. So we will do that next. So we have the R squared, and we are multiplying then different terms. So we multiply with 1 so that we get the original R1 term, and then we have the small x squared plus small y squared, and now we divide this with the capital R squared, and then we have the latter term of this form. So essentially we just took R squared to be a common multiplier, and that's it. Nothing's changed there. And now the good thing here of this way of writing things out is that we can really simplify this by noting that the small x and small y are way smaller numbers than the capital R. And this means essentially that we can use the Taylor's expansion approximation on the square root of 1 plus a, where a is a smaller than unity in size. So essentially we can approximate things by just taking this approximation. And now we are applying that. We can take the square root of both sides so that we end up something where we have 1 plus something. And now this is our a term here. And this we say that this is actually small, since with this we can see that the capital R squared must be always larger than this and this and so forth. So this is what we do. And we now can take the distance R into a form that R is basically just R now. And then what we have on left And now we have used the previous approximation. And here, please, that's the reason why we have the 1/2 here and also here. So that's where 2 arises here. So nothing strange there. We just approximated the square root. That was a form of 1 plus a, where a is actually way smaller than unity. And now we see that we can we can write terms differently. So we can just write the r inside the parentheses again. And we see now that it's in fact the second term's numerator that is actually very small compared to the denominator. So for example here, especially here, we can see that this x squared plus y squared, this is always very much smaller than 2r. And this is nice because then we can really neglect these term altogether in our phase term. And now basically we recall that the maximum size of the aperture A is not large, and then we can write that the kind of largest possibility for the second term to have essentially will be of the order that we are replacing x and y with the A. So basically we then have a squared divided by 2r, or maybe we should have 2 times a squared here, but essentially that's the kind of largest we can have for that value. And in this case, this doesn't really matter to the phase evolution of the wave. So that basically when this condition applies, the phase function doesn't really change much when we are changing the coordinates. So k times a squared divided by 2r, and this is basically the phase evolution. So this is the exponent ikr. So we have the kr there inside the exponent. So we have the k, and here we have the r term there, the distance term. And this is the kind of largest value that we can have. And since a is small compared to r, this simplifies things. So we can write the k, that of course is equal to 2 pi over lambda. And then we have the a squared divided by 2 capital R. And then we get rid of the 2's. So what we have left is we have pi times a squared divided by lambda r. And this is essentially that we can use now to derive some kind of a regime where what follows is an okay approximation to make. So this equation now we can really use to find a condition where the Fraunhofer diffraction is a valid approximation to make. And essentially that gives me a condition that the capital R is greater than a squared divided by lambda. And this is a kind of criteria where if this is fulfilled, then it's okay to consider the Fraunhofer diffraction and not, for example, the Fresnel diffraction. And when this above condition applies, then the second term's contribution into the overall phase term is very small, negligible, and then that means that then the distance to the observation point, the r reduces into that the r is only the capital R minus the third term in the equation we had in the previous slides beginning. So essentially we vanished the term, it's negligible, the term that is small x squared plus small y squared divided by 2r. And this is now how we approximate r inside our phase function. And now we're looking at the observation point. That's where light is being diffracted. And here, essentially how it's being diffracted, that it's a spherical wave originating from the differential surface element location, ds. And now we can really write our integral, or maybe better, just like the kind of I'm confused why I don't have an integral here, but let me put in the equations here first. So essentially now, yes, so this is a wave originating from this one single location corresponding to the differential surface element. So essentially like in a one location of the aperture. And indeed, if I only have a single location, I will only get a single spherical wave originating from there. And now on the left-hand side, I'm calculating basically how this spherical wave looks like at my observation point. And this is how the phase function has now been approximated by just taking use of this condition and simplifying things. So this is what we now have here. And of course, this is for a single small location in my aperture function, so corresponding to the differential surface element ds. So that's why I don't have the integral. And now what I want to do is that I want to calculate the total field in that location. So okay, yes, I'm using a notation E tot as in the total field at the point xy. And now we calculate this by then solving an diffraction integral. So now essentially we are summing over the aperture function of all of these waves, spherical waves that are originating from a different differential volumes. So basically we are now integrating our aperture function with respect to the dx and dy. So this is how we do things, and this, when we do the summation, so essentially solving the integral, we get the total field, the total superposed field in that location. The phase term, especially the IKR term here, can now be taken out from the integrals because it doesn't really change from x and y. It doesn't depend on them. And then r also, we do not need to change that much because r is much larger in value than the locations at the aperture. So they are basically constants with respect to the integral, so we can take them out. They are constant with respect to that integral. This is approximately true. And then what we have left is that we have the kind of original field distribution at the aperture, depending on the coordinates x and y. And then we have this kind of integral kernel, which looks not anymore like a spherical wave anymore, but rather like a plane waves propagating in different directions. So this is how our diffraction integral now has been simplified into. And this is nice because it doesn't look that awful anymore. And in fact, it actually starts looking beautiful because it starts resembling a Fourier transform. So this is nice. The functional form, in fact, like I already said, corresponds to the two-dimensional Fourier transform of my aperture-dependent field distribution EA. So this is super beautiful, like fanfares, please. Like again, we are seeing that the awful and elegant and beautiful mathematics of Fourier transforms, like we are facing them again. And we see now that in fact here, what we have is essentially that the diffracted field somehow seems to be related to the aperture function via a Fourier transform. But of course, this is an introductory course. So in case you do not yet love Fourier transforms, then don't worry, we do not deal that much with them. Basically, we just look from the Wikipedia some properties of Fourier transforms and maybe some common transformations, and that's it. We do not deal much with the Fourier transforms on this course. On this course. So like Douglas Adams was saying, don't worry, don't panic, things will be fine. So now we have a Fraunhofer diffraction integral, and the integral was solved to be of a form that we have some kind of common phase factor here. This looks like a little bit like a spherical wave. So when we go further off, the amplitude goes down because we have the inverse of r dependence here. And then we have the actual Fraunhofer diffraction integral that looks like this. And lo and behold, it looks like a 2D Fourier transform. And this can be interpreted using two different ways. So I'm almost done with the lecture now. So the first interpretation, and this is a little bit more about the kind of physical interpretation, is that we have variables that are associated with the observation point. So I have capital X divided by R and capital Y divided by R there in my integral kernel. So essentially here I have capital X divided by R, and the same thing for Y. So these we can understand also as angles. And when we are understanding them as angles, like we can kind of see that this Fraunhofer diffraction integral in a way, like we are summing light that are coming from different directions into the location point. So this would be my physical interpretation of the Fraunhofer diffraction integral. So we can still, I can picture in my mind that I have an aperture, and rays of light are propagating through all different locations of the aperture. And now I'm just basically summing them into this different point, and that's it. So I can kind of understand that these different kind of signs corresponding to different angles, direction into which these incident light, rays of light are being propagating into the observation point, they are of this form. So that then I can really have a kind of nice and graphical and physical interpretation of this otherwise maybe obscure piece of mathematics. And now if I would be using a lens, like the diffracted light distribution, so essentially the irradiance pattern of light, I could even image that, and that would be nice. And more on this, of course, in the geometrical optics part. So for example, like now with this physical picture in mind, okay, since we have rays of light and they kind of, we can interpret that they are coming at the given angles. In fact, I could also just think that instead of like considering a diffraction pattern, what about I would have, instead of an aperture, I would have a radio wave antenna, some kind of source that would be emitting electromagnetic radiation, and I would want to understand what kind of radiation pattern it would have. And this kind of math would provide me some kind of inkling of understanding of how that kind of situation could also be understood, or measuring, how we could measure the radiation pattern. So in a way, we see that by understanding diffraction of light, we can also understand how tiny sources of light emit light nearby our source plane, source points, so that we can get information by looking at the diffraction of what happens at the source. And more on this, by the way, in our course on solid state physics, where we will be treating electron diffraction and X-ray diffraction in particular from small, atomically small objects, so basically from crystals. And here and there, we will be dealing a lot more with these mathematics, and we will in fact deal with the mathematics on a level that we can really actually understand, that we could measure even the periodic crystalline structure of different kinds of solids by looking at the diffraction profiles caused by them when we would be doing experiments. But of course, this is beyond our course, and the scope is different, but the same kind of math will be generalized and applied there in a different course. So if you're interested, solid state physics, like knock yourself out, where we are treating different diffraction integrals there too. Okay, back. We were getting back into the optics course. Sorry about this. I'm somehow always like getting lost into other things on my mind. So the second interpretation that we can formulate here and have is that it's really more on the kind of mathematics oriented. And now we can look that we have the observation point coordinates x and y, so that they are very small compared to the distance between the diffraction source. So basically, and the observation point. So basically, this means that the r is approximately z. And then if you would be placing a camera or a screen into the observation plane, so where the z equals capital Z, we would directly be able to measure the diffraction pattern E dot xy caused by the aperture field here. Sorry, I don't spoil the fun now. So basically, here I can scrap this guy, and then I can just simplify that this is unity, no change will be there, and then I could really measure this right away in a given plane z equals z, and then I would know that this would be the diffraction pattern caused by this aperture function. And the beautiful thing here is that the mathematics says to me, because of this functional form of this integral, that if I would take just mindlessly, and this is just a mathematical operation, I would take a Fourier transform of this aperture function EA, that is now a variable depends on the variables x and y. Now I would take the Fourier transform, and now I would be in the spatial frequency domain, so I would be describing exactly the same kind of function, but now not in the x and y coordinates, but using spatial frequencies kx and ky, and this would be something that I would be able to measure if I would be measuring the total field here. And if I would be somehow magically able to measure the actual field and its phase, and not just the irradiance distribution as would be all normally the case. But in principle, this is super beautiful, because we now see that in fact, if we would be able to measure the whole phase and amplitude information of my diffracted field, I would inverse Fourier transform this guy, and I would actually get information of this aperture function. And this is super interesting, because what happens if I would not know what is the shape of my scattering object? And this is indeed the case when I have solids and I'm doing X-ray diffraction on them. I do not know how this guy looks like, but I will be able to measure this guy. And then if I do Fourier inverse Fourier transform magic and other magical things so that I actually can solve the phase problem associated, I can actually get information of this guy if I do not know this. And this is my second interpretation on this, that they instead of like thinking about the physical interpretation, we can only purely look at the mathematics and how this integral looks like. And this also provides us a lot of useful things that we may be able to like apply in the future if the need arises. So I thank you for listening this lecture. I hope you enjoyed. I was speaking about Fraunhofer diffraction, and in the next lecture I will be applying this Fraunhofer diffraction into few simple scenarios of having aperture shapes that are simple and we can easily perform the integrals. So thanks, and please join me quickly and in hearing more about Fraunhofer diffraction in the upcoming lectures. So thanks and bye-bye.